So is my screen visible?
Yes, sir.
Yes, sir, your screen is visible.
Yeah. Thank you. Right. So the agenda for today is to cover recommender systems, which is applications of this machine learning. And now it is becoming evolving like an area in the machine learning. Recommender system is also like one of techniques in machine learning. Right. So as you all know, we are currently living in a data era where a huge amount of data is collected and stored every day, isn't it? So that is because our interaction with World Wide Web has been increased. So we perform various tasks with the help of World Wide Web, isn't it? So we read books online, we read news articles online, we procure utilities online, we book cab online, we order food online, we purchase things online, we attend classes online. So our interaction with this internet has been increased, right? And the competition among the vendors offering various services and your interaction with these systems producing a lot of data. A lot of data has been accumulated, lots of data is being collected daily. Huge amount of data is collected daily and stored. Okay, so in the face of this growing quality of the data, there is a information overload problem is coming. So there is a confusion to the user because there are so many options for the user. The confusion to the user what to buy or opt for. Okay, so the user is facing information overload problem in respect of this growing amount of data. Okay, so to avoid this information overload problem and present the user with interesting items, the recommender systems concept came into picture. Right, so um, it just avoids the overload information overload problem by presenting the user with interesting items. Okay, so these recommender systems you may be using it daily without even knowing that it is a recommender systems. For example, in YouTube, when you watch some video, it recommends some set of videos to you. Okay, so that's the recommender systems. The concept behind that is the recommender systems. It evolved when you like some video or when you skip some video, YouTube learns from it and make the recommendations according to your preferences. And these recommendations evolves with your preferences, right? Similarly, when you purchase something, some item, it recommends some set of items to you. You may also like this, or those who have bought this also bought this. So these kind of things we see everywhere, right? In e-commerce sites also we see when you purchase something in Flipkart or Amazon, you will see this kind of recommendations. When you watch some video, you see these kind of recommendations. When you open Facebook, it recommends friends to you, right? So these kind of recommendations, recommender systems we see everywhere nowadays. Okay, so we are familiar with them. Okay, but we not may not be knowing them, but they are all recommender systems. So in this class we're gonna cover introduction to recommender systems, different paradigms of recommender systems. Different paradigms are collaborative filtering, content based, knowledge based, and hybrid approaches, right? And then we'll see evaluating the recommended systems, and we'll have uh, a small practical session, right? Right. So recommended systems, as I've told you, data is everywhere, and there is a need to derive some meaningful insights out of this data. Why we need to derive some meaningful insights out of this data? To For the organizations for better functioning, right? And to assist users in decision making process. Okay, to improve the quality of the decision that the user make, right? And the amount of data that we have is enormous, and large amount of data leads to information overload problem. So there is a need for some assistance in the form of recommendation in our day-to-day life. right? So there are various recommendations. Like for example, if you see this figure, uh, so excuse me if I. So if you see this figure, there are two users. One of the user have already ate pizza and fried rice, probably that fried rice, and the other user pizza, fried rice, and coke. Okay, so these two are similar, no? Those who have purchased fried rice and pizza to, I mean, commonly they're similar users, right? Right. So this user additionally have purchased coke also, and this user has not purchased that. You recommend that to him. Okay, so this is the one kind of recommendation. This is a collaborative filtering based recommendation, right? So based on your similarities, you identify the user and recommend what is popular among this pair, right? So recommender system. Okay, so the world is moving from one size fits for all to personalized and tailor-made solutions, isn't it? So that is, it's not that you fix one size, so this is the size for everyone, right? Instead of that, we are going for the personalized, tailor-made solutions. So the each and everyone preferences may be different. So when you're watching YouTube channel, the set of recommendations that you get may be different from the set of recommendations that your friend may get, right? So this is one kind of recommendation, this example figure that you can customers also watched. So when you're watching something, Lord of Rings, the two towers. So you've got some set of recommendation here. As you can see here, Harry Potter, Lord of Rings, some other movies it is recommended to you. So those who watched also watched this. So that's what it is recommending, right? So those who watched this means customer who have a similar preferences like you, right? So because he has also watched, you are also watching this. So the customer who have a similar preferences with you also watch this. Okay, so if you are interested, you may watch. So that's what it is saying. Okay, similarly here if you see frequently bought together. So when you are purchasing something, it is displaying to you that frequently bought together. So it means that it is recommending these other two items to you, right? So book recommendation, if you see, how do you do that? You have some collection of books and your preferences about those books, whether you like them or dislike them. Thumb up means like, thumb down means dislike. Okay, and these are the books. So this information is given to a machine learning algorithm or recommender algorithm. Okay, the books and the corresponding preferences. Book and the corresponding preference. Book and the corresponding preference. So given new book, right, you should be able to determine whether the user would like it or not. Right. So this is a simple recommender system. Okay. So precisely, recommender system help to match users with the items. That is to ease the information overload problem and in sales assistance, right? So this can be seen as a function. The recommender systems can be seen as a function that maps the items to a user. Okay, so given user model means user ratings about some items, user preferences or his demographics or situational context, all this comes under user model. Okay, your recommendation algorithm use one or more informations about this. It may use ratings, it may use demographics sometimes, it may use situational context, or it may use all of this information sometimes, or it may use some part of this information based on the exploitable data. Right. So user model has the ratings, preferences, demographics, situational context. All this information is there in the user model. And also items with or without description of the item characteristics. So we have given basically we have given users and items, user model and the items. What we need to find, we need to estimate the relevance score or use it your relevance score, how relevant an item is for a particular user. Okay, so this function taking user model and items and returning relevance score. Okay, so that's what I'm trying to tell you. So Recommender system can be seen as a function which receiving user model and items as the input and returning relevance score or the ranking as the output, right? So there are different paradigms of recommender systems. Let us go through them, right? So the recommender systems reduce the information overload problem by estimating the relevance. So the output of the recommender component is the relevance score. So the how relevant is item 1 to user, how relevant is item 2 user, to the user, and so on. Okay, and this score is some numerical score. The highest is more relevant, right? So that is how it estimate the relevance score. And this relevance score can be a rating prediction or it can be some score which is useful for ranking the items, right? So both are possible. Either it is a rating system or rating prediction system or a ranking system. All right. So personalized recommendation systems consider the user profile and contextual parameters and they estimate the relevance score to that particular user. So if you consider the group recommender systems, it makes the recommendation to the group of user in contrast to a single user. So the group can be a family, group can be friends, group can be office people, colleagues, right? Group can be anything. Group can be some tourism group, right? So it makes recommendation to a group of people. So in that case, it considers the preferences of all the individual persons and make the recommendation to the groups as that most of the members in the group are satisfied. Right. So that's the objective of the group recommendation system. We're not discussing about the group recommender system in this session. We are only discussing about the personalized recommendations in which we only consider the preferences of the individual user. Right. So there are different paradigms. Collaborative filtering systems picks up what is popular among the peers. Okay, so it considers the similar users and picks up the items that are popular among the similar users. Right, the one we have seen, right? The Coke example in the very first slide. So that is an example of collaborative based filtering technique. So for this, community data is required. Okay, because you have to identify what is popular among your peers, you have to identify the similar users. So to identify all that, community data is required. The information about the other users is required, right? So what they have watched or what they have consumed, how they rated these items, all this information is required in case of collaborative filtering. Right. In the case of content based, it recommends more of what you have liked in the past. For example, if you have liked comedy movies in the past, it will recommend comedy movies to you in the future. If you have liked drama movies in the past, then it will recommend drama movies. If you have liked friction novels in the past, it may recommend friction novels to you in the future. Right. So more of what you have liked in the past. So for this, you require the product feature or the characteristics. So each feature, each product or an item is described with some set of characteristics or the features. Based on these features, you will identify the similarity between your history of consumption and the candidate items that candidate items for the recommendation. Alright, so for this product features also required. And knowledge based, tell me what fits based on my needs. Right, you have some needs. For example, you may require some 7-seater car. I mean, based on your family size. Right, you may have preferences like black car. Right, so based on your needs, it makes the recommendation to you. Right. And hybrid is a combination of various inputs and a composition of different mechanisms. Combining multiple models in some way or the other will result in hybrid models. Right? So these are the different paradigms in the recommender systems. So is that clear so far? Uh, is that clear?
Yes, sir.
Yeah, thank you. So, yeah, these are the different paradigms. Let us try to discuss each one of them one by one. Let us discuss the collaborative filtering technique. So this collaborative filtering technique is the most prominent approach to generate the recommender system. Most of the existing current e-commerce sites use this collaborative filtering, right? And it is well understood, and there are lots of algorithms in this. Lots of hundreds and thousands of algorithms exist in this collaborative filtering, and this is applicable for many domains such as books, movies, DVDs, etc. Right? So the idea is use the wisdom of the crowd to make the recommendation. Wisdom of the crowd means so their preferences, like the users who are similar to you, you use their preferences, their choices to make the recommendation to this user, right? So the basic assumption here is that users give rating to a catalog of items, either implicitly or explicitly. Okay, so what is this implicit and explicit ratings, right? So let us try to see with examples. Explicit rating means when you purchase some item, it asks you for the rating. Okay, so like, would you like to give 3 stars or 4 stars, 5 stars, 2 star, 1 star? Okay, you might have rated some items also in some e-commerce sites. This is explicit rating, right? What is implicit rating? You may not be explicitly saying that you liked it or you didn't like it, but it infers from your actions. Like for example, if you skip video in YouTube, okay, it means that you might not have liked it. Okay, if you're watching it till the end, it means that you liked it. Okay, so it is inferring from your actions. That is implicit feedback that you are giving to the systems. So the assumption here is that user gives his preferences to the items implicitly or explicitly. Okay, so this is one assumption of the collaborative filtering. Okay, and if this is not there, I mean, giving preferences by the user is violating. I mean, if it cannot be captured, then collaborative filtering may not work. Alright. So the second assumption is customer who had a similar taste in the past will have a similar taste in the future also. Like, okay, so for example, X and Y. Okay, let's say Brinda ma'am and Prashant has a similar taste now. Okay, so it is assuming that in the future also they have similar taste, similar preferences. So that's what the assumption is, right? So these two are the assumptions. Then if you take the pure collaborative filtering approaches, the input is only a matrix of given user item ratings. So user and item rating matrix. Outputs are prediction indicating to what degree the current user will like or dislike a certain item, or top n list of recommended items. So it is either prediction or ranking of the items, prediction of the rating or ranking of items. So if you see the collaborative filtering, they aim at predicting user interest in some given items based on their preferences so far. So if you see this, is my voice audible to you? Somebody is saying his voice is coming.
Yes, sir.
Yeah, okay. All right. So yeah, so if you see this, this is what given to us, user item rating matrix. Some places we have got some entries like 4, 1, 4, 3. So these are the preferences, ratings that the user is giving to a certain item. So the columns are the items, item 1, item 2, item 3, so on. And these are the users, user 1, user 2, so on. Okay, and this is the rating that the user 1 is giving to item 2. And few of the entries are zeros. It means they are the unobserved items. User have not consumed them yet. Okay, so the idea is to recommend some movies out of these unobserved entries. Like for example, user 1 has not watched item, not consumed item 1 or item 3 or item 4, so on, right? Wherever zeros are present. So idea is to make some recommendations from out of these unobserved items, right? Or predicting the rating that how much this user would give to a particular item. Okay, whether he would give a rating of 3 or rating of 4, rating of 2 or rating of 1. If the prediction is high, it means that he will like the item probably. Okay, so you may be interested in that item probably, and we make the recommendation according to the highest to lowest rank rating preferences according to the prediction, right? So the question is, will the user I like movie J or not? Right. So 0 means will he like this item or not? So it is mentioned movie here. If it is movies, movies. If it is items, you generalize it to items. If it is a movie recommendation domain, items are equal to movies. If it is a book recommendation domain, items equal to books and so forth. Right. And this rating can be one of the ratings 0 or 1 to R. There it is in a 5 scale. So 1, 2, 3, 4, 5 are the ratings. 0 means unobserved entry. So collaborative prediction models can be categorized into two different types: neighborhood based collaborative filtering, model based collaborative filtering or prediction. Excuse me. So in the neighborhood based collaborative filtering, we select the subset of users based on the similarity with the target user. So we pick up the users that are similar to the target users to whom you want to make the recommendation, and combine their ratings to produce the rating for the target user. So you take their ratings for a certain item and combine the rating to produce the rating for the or to predict the rating for the target user. So this is the procedure that we follow in the case of neighborhood based collaborative filtering. In case of model based collaborative filtering, we have a latent factor model. This is one of the model based collaborative filtering that we're gonna discuss. Latent factor model means it assumes that there exists an unknown low dimensional representation of users and items. Right? When you find user item similarity, it can be modeled accurately. We'll see that example, then you will understand it better rather than describing it like this way. Right? So we'll see in the coming slides. If you don't understand, please let me know that time. So let us see user-based nearest neighbor collaborative filtering technique. So the basic idea is we have given a target user. We also call him as an active user. Target user or active user are same. So Alice is the target user for us now. And an item I not yet seen by Alice. Now the question is whether this target user would like this item I or not. Okay, so to identify that, in case of user-based nearest neighbor, what we do is that we find a set of users who like the same items as Alice. It means that we are trying to find out the users who are similar to this target user Alice, right? And we take their ratings to predict for Alice rating on item I. Okay, so they might have already rated I, right? So we take their ratings for I to predict the Alice rating for I. Okay, and we do this for all the items Alice has not yet seen and recommend the best rated items. So we predict the items that are not seen by Alice. We rank them according to this predicted rating and we recommend the top K items to this target user. Right? So is that clear? So if you see this, he is the target user. We are finding the similarity with all the other users and we are considering the closest users or similar users or nearest neighbors, whatever you call. And we use their ratings for this item to make the prediction for Alice rating on that particular item. So the assumption here is that if user had similar taste in the past, they will have a similar taste in the future, and the user preferences remain stable and consistent over period of time. Okay, consistence and stable means if you have same preferences now, you will have similar preferences in the future also. If two users have same preferences now, they will have a similar preferences in the future also. So that's what the assumption is. So we'll see the example. Here we have a database of ratings, right? And Alice is our target user and he has not yet seen this item 5. And the task is to predict this entry, whether it is a 1 or 2 or 3 or 4 or 5. Okay, so determine whether Alice will like or dislike item 5. So which Alice has not yet rated or seen, right? So according to this procedure, what are we doing? We are trying to find out the users who are similar to Alice. right? So based on their rating information. So what rating that user has given for a particular set of items, right? For example, Alice has given rating 5 and user 1 has given rating 3 for item 3, right? So and guy has given 3, this guy has given 1, like that. So you see the rating pattern to determine the similarity between the users. What is their rating pattern? Do they have a similar rating pattern or not? So that's what we're gonna see. So when we say find out the nearest neighbors or the similar users, some first questions that are coming in our mind is that how do we measure the similarity between the users and how many neighbors should be considered? Okay, so and how do we generate a prediction from the neighbors rating, isn't it? So these are all the questions that comes in our mind, right? How do we measure the similarity between the users and how many similar users we have to consider, and once we identify the similar users, how do we make prediction from their ratings? What is the formula that we should use? Okay, so these are the initial questions that comes in our mind. So let us see one by one. The popular similarity measure in the case of user-based collaborative filtering is Pearson correlation. Pearson is the popular and proven to be working well in the case of user-based collaborative filtering. But it is not limited to using only Pearson correlation. There are various other similarity strategies. But it is proven to be working well in the case of user-based collaborative filtering. So let us see what is Pearson correlation. So it is trying to identify the correlation between the rating pattern, right? How correlated both of these rating patterns are. Suppose if you want to find the similarity between two users A and B, you take their ratings. Okay. So here rating AP is the rating of user A for an item P, and capital P is the set of items rated by both A and B. So what are we doing? We are computing. I'll ask a simple question before I explain this equation to you. Suppose if I give a rating to a certain item which is greater than my average rating, what is that means? Do I like that item or dislike that item?
Like that item.
I like that item. If I give the rating which is less than my average rating, which means I dislike that item, isn't it? So now to see whether two users have liked the item or disliked the item, you take the average and subtract the rating from subtract the average from the rating. Okay, so you're taking the commonly rated items, and for each item you're subtracting that rating from the average. So this gives whether user A likes this item or dislike the item. Okay, if it is negative, it means that he disliked the item. If it is positive, he liked the item. Great. And similarly, this gives whether user B likes that item or dislike the item. If it is positive, he may like the item, and the amount, the number indicates how well he liked that item or how well he disliked the item. Okay, if it is a big positive number, he like the item very much. If it is a big negative number, then he may dislike the item very much. Big means here, according to that scale, it is within a scale of 1 to 5 itself. Right. So now the question is, if both of them are positive, what is that it means? Both of them like the item. Okay. So the resultant will be positive. If one is positive, the other one is negative. What is that means? Probably these two users' rating pattern is different, isn't it? They may not have the same rating pattern. Agree? Right. So you do this for all the items and take the sum over. And this is the variance within the user A profile. This is the variance within the standard deviation within the user A profile, standard deviation within the B profile. So what is that Pearson correlation is measuring? Whether the users A and B have the same rating pattern or not. Okay, if they have the same rating pattern, then this similarity will be positive. If they do not have the same rating pattern, it may be negative or zero. right? So let us see that. So the possible similarity value is between -1 and 1. 1 means highly correlated. Negative -1 means highly dissimilar, right? So when I measure the similarity of Alice with respect to user 1, I've got the similarity of 0.85. Here similarity, this comma is dot, just make that correction. This is dot. Similarity is 0 with respect to user 2. Similarity is 0.7 here, and similarity is minus 0.79. There's a question in the chat box. And Pearson correlation be used for feature selection? Yes, ma'am, can be used. Right. So we have measured the similarity between the users. Right. So who is more similar to this Alice and who is more dissimilar to this Alice?
User 1 is similar.
User 1 is more similar and user 4 is more
Dissimilar.
dissimilar to the user. But if you observe the Alice rating and user 1 rating, they didn't give the same rating, isn't it? If the Alice is giving 5, the user 1 is giving 3. Alice is 3, then user 1, 1. Like this. They have got different ratings. How do you think they are similar?
Proportionately,
Average
propor-
rating.
I think proportionately their pattern is same.
Proportionately their pattern is same, right?
So,
So yeah, so very good. So it means that they've got the same rating pattern, similar rating pattern, though the rating is not same. So this Alice may be somewhat lenient in giving the ratings, but user one may not be lenient in giving the ratings. He is a very strict person. Okay, if you like it very much, then you will give 4. Okay, but this Alice is not like that. He is a very, I mean, easily satisfying person. Okay, so even if it like, yeah, I mean, even if he likes it to the small extent, then he gives a rating of 3. Okay, so something like that. He is the lenient user, whereas the user one may not be so much lenient. But if you observe the rating pattern, they have got the same rating pattern, right? So according to this average concept, so the items are above their average or below their average. Item rating is above their average or below their average for both of them, right? So if you observe the rating patterns, it is something like this. Alice and user 1, if you see the Alice ratings and user 1 rating, like this plot, you can observe that they have got the similar pattern, right? So if it is increasing, this is also increasing. If it is decreasing, this is also decreasing. Like that, they have got the similar pattern, Alice and user 1. Whereas if you compare this pattern with the user 4, Alice and user 4, so this is user 4 rating. So if you see this, they've got different patterns. If Alice is giving 5, this guy is giving 1. If he is giving 5, then this guy is giving 1. Opposite. Okay. So they have got contrasting preferences. Right? So that is what basically this Pearson correlation measures. So it works well in usual domains compared with the alternative measures such as cosine similarity. So now the question is, yeah.
sir, but correlation is more or less similar to cosine measure, na, sir? I mean, why the difference here? Because what we
Nahi,
are doing in
they are
correlation,
similar. That is why we are comparing, no?
yes, sir.
There is no doubt they're used for the same purpose.
Yes, sir.
Okay. But what it is
Because
saying, in usual domains, usually when you apply it practically,
yes, sir.
it is Pearson correlation is working well. That's
Okay.
what. Yeah. So in that too in the case of user-based collaborative filtering. But
Yes,
if
sir.
you
But
go for the item-based collaborative filtering,
okay.
maybe some other measure work well.
Because why my doubt came because correlation is the numerator is nothing but dot product between two vectors, where the denominator is nothing but magnitude of two vectors. The both are same, more or less. Only domain.
Yeah, similar. They
Yes,
are similar,
yeah,
but this is proven to be working well for this particular case.
yes, sir.
Okay, so that is
Okay,
when you apply practically.
yes, sir.
Okay, yeah. So
Okay,
that's
sir.
what it
Okay, sir.
is.
Yes, thank you, sir.
And this cosine similarity, as you have mentioned, that is also used for similarity, and it is proven to be working for item-based collaborative filtering.
Okay, sir.
So we'll see that in the coming slides.
Yes, sir. Thank you, sir.
Yeah. So once we measure the similarity, how to make the prediction? So we've got the similarity measure, how to make the prediction, right? So we take the neighbors. Neighbors can be based on the top k neighbors, or it can be if the similarity greater than certain threshold, you can pick them, or you can consider all of them also sometimes. Okay. So we take the neighbors, n is the neighbors, and we consider their preference a particular item. Okay, suppose if you want to measure this prediction of user A on item P. Okay, so we consider the neighbor's rating on P, whether it is above the average or below the average. Okay, so this is neighbor's rating on this item P. We are subtracting it from his average. Okay, if he is like this item, then this will be positive. If he dislike this item, this will be negative, right? And multiplied with the corresponding similarity. So, I mean similarity between A and B. If he is highly similar, it means we are giving a high weightage to his preference. If he is not that similar, then we give low preference to that corresponding neighbor, right? So the weighted uh, uh, rating difference we are taking into consideration and adding that to the current user's average, right? So among the peers, on an average, if they like the item, then you add some positive quantity to this average. It means that the user A also will like the item. On an average, if this is a negative quantity, it means that in the pairs, among the pairs, they'll dislike the item. So there probably this user A also will dislike the item. So that is what the intuition behind this prediction. So have you got it? Have you got it? The
Yes, sir.
prediction method? Yeah, right. So this is how you can predict target user rating for a new item P. Like this, we find out the rating for all the unobserved entries and we rank them according to this predicted ratings. Okay, once we rank them, we recommend top k items to the users. Then the item-based collaborative filtering. So the basic idea is use the similarity between the items to make the predictions. For example, look for items that are similar to item 5. So because we want to make prediction for this item 5. Okay, so look for the items that are similar to item 5. Suppose if you identify that item 2 and item 4 are similar to this item 5 using some similarity measure. Then use Alice rating for those items to make the prediction for item 5. So we use these two ratings, Alice ratings for these items to make the prediction for item 5. Okay, so here cosine similarity produces better results in the case of item to item filtering. And ratings are seen as a vector in n-dimensional space. And similarity is calculated this way. This is cosine similarity. After adjusting it to this particular application, this is the cosine similarity, which is very similar. Only thing that is changing is that is calculated column wise. Here it is row wise. Sorry, reverse way I told you. That is calculated row wise. Here it is column wise. So the making prediction also similar. So we use the similar items rating and multiply it with the corresponding similarity and take the weighted average. Okay, and here if you see the neighborhood size typically limited to a specific size here. When you are considering the similar items, you restrict this neighborhood size to certain size. So not all neighbors are taken into account for the prediction. So typically in the real world situations, when it is practically implemented, the neighborhood of 20 to 50 neighbors seems to be reasonable. So this is from this reference. Okay, so some analysis on this MovieLens dataset. MovieLens is one of the standard benchmarks dataset in the case of this recommender systems. So analysis on that dataset indicating that 20 to 50 neighborhood size is reasonable. Alright, so this is how we make the predictions in the case of item-based collaborative filtering. We have seen user-based collaborative filtering, then item-based collaborative filtering. The problems with this are cold start problem is there. Suppose if I have got a new user who has not rated any item, how would I make recommendations to him? Right. Suppose I've got a new item, none of the users have rated it. Right. How would I make the recommendation? How would I make, how would I recommend that item? Okay. So there is a cold start problem here in the case of collaborative filtering. So the straightforward approaches to solve the cold start problem is you force the user to rate set of items. Like this I have also done. I think when I was registering for Netflix or something, it forced me to rate some of the items. I do not remember exactly the number. I think around 10 movies it has asked me to rate. Okay, so at the time of registration itself, it is forcing the user to rate the set of items. So this is one way. Or use another method in the initial phase, which doesn't suffer from the cold start problem, like content based or demographic based, okay, or simply non-personalized recommendation. Some popular items you can make recommend at the initial stage. Okay, gradually when the user is liking or disliking those items, you can learn from his preferences. Okay, this is another approach. Initially, at the beginning stage, you can use a different approach to make the recommendation. And when you get the sufficient number of references from the user profile or the item profile, you make the predict based on the collaborative filtering approach. Another way is default voting. Assign some default values to the items that only one of the two users to be compared as rated. Right. So when you're comparing two ratings and if only one of the user has rated them, then you assign some default rating to it. Okay, default rating may be average rating or something like that. Right. These are some straightforward approaches to solve the cold start problem. Alternative is we can use a better algorithm beyond the nearest neighbor algorithm. Okay, like other approaches that we're going to discuss in the coming slides, or you can assume transitivity of the neighbors. Suppose if you some item is missing, okay, so suppose if you want to make prediction to the Alice, okay, his nearest neighbor is user 1. Okay, you want to make prediction based on this rating by user 1. Suppose if this is missing, what would you do? You find out the users who are similar to user 1. Okay, he might have rated it. So you assume the transitivity in the similarity. If Alice is similar to user 1 and if user 1 is similar to user 2, Alice is similar to user 1. Right? So therefore, you make the prediction for user 1 based on user 2 ratings. Once you get this rating, you use this rating to make the prediction for Alice. Okay, so this is how you can assume the transitivity of the neighborhood and make the prediction. Okay, so this is another way of handling cold start problem. Then we're going to discuss model-based collaborative filtering. Model-based collaborative filtering. So can anyone tell me what is the difference between memory-based machine learning approaches and model-based machine learning approaches? Anyone?
Uh, we may uh, we may learn a function for the in model based things that gives us a relation between similar recommendation coefficient and the given inputs, so that we need not we can store only the particular parameters, the model parameters, instead of all the memory.
All right, very good. So in the case of model-based machine learning approaches, what are we doing? We're representing the data in a concise format using some function or a hypothesis or a model. Like if you take linear regression, we're representing the whole data set using theta naught plus theta 1 x. So once we get this model, you can throw away the data. You don't need data to make the prediction. You just need this theta naught and theta 1 to make the prediction, isn't it? So you're representing the data in terms of a model. Once you get the model, you're using this model to make the prediction. Whereas in case of memory-based approaches, you store the whole dataset and then at the time of prediction, you make use of this dataset to make the prediction. Okay, either by finding the similarity or similar users or k nearest neighbors. All these are the examples of the memory-based approaches. Whereas in case of model-based approaches, we just take the model from the data, we learn the model from the data, and we use that model to make the predictions. So now we're gonna see one of the model-based collaborative filtering technique, that is matrix factorization. So matrix factorization, what is matrix factorization? You are given a user item rating matrix. Why? We have seen one of the user item rating matrix in our previous slides, in which some of the entries are observed, some of the entries are unobserved, zeros. Okay, and the task is to predict this unobserved ratings, unobserved entries, right? So what this collaborative filtering using matrix factorization is doing, that it is learning two latent factors, user latent factors matrix and item latent factor matrix. So it is learning two matrices U and V such that when you multiply both of them, the resultant is closely equivalent to Y for all the observed entries. So remember this. So what it is learning? It is learning two matrices U and V such that U multiplied V transpose is nearly equivalent to Y for all the observed entries. Okay, so because it is reducing the difference between the actual and the predicted for all the observed entries, it is also assumed that it is accurately predicting the unobserved entries. So did you get my point? It is trying to learn the two matrices such that the predicted value is equivalent to the actual value over all the observed entries. Great. So therefore, we assume that it will also predict for the future, unobserved entries. Right. So it assumes that there are some low dimensional latent factors which represents the users and the items. For example, if this is a rating metric, assume that it is a binary rating metric where we have only ones and minus one. One means like, minus one means dislike by the user. And there are some unobserved entries. So when I find the latent factors of this two matrices U and V, you can see that this latent factor may represent some quality in that user or an item. Okay, we do not know what are those quality or characteristics of the item or a user. So let's assume, for example, if I learn two latent factors, the first latent factor may be a drama and the second one may be a comedy. So the entry represent to what extent the user will like or dislike the corresponding characteristic, whether the user will like drama or whether the user will like comedy. So this is represented in the latent factor. And the V1, which means the items also have got these similar characteristics. So this is drama, this is comedy. So when you multiply this with this, so what would happen if both are positive? Then you will end up with a positive results. It means what? The user also likes drama and the item also has the drama content. So therefore it is positive. If both are negative, then also it is positive. It means the user doesn't like drama and the item also doesn't have drama content. Right? So in that case also it is positive to the user. So like this, it learns the low level representation of the users and the items. So there are some hidden latent factors which represents the preferences of the users and characteristics of the items. We do not know what are those preferences, what are those characteristics. You're just learning them. Okay, we cannot interpret that first column is drama, the second column is comedy, third column is action. We cannot interpret that way. Okay, just for an understanding, I gave you this example of drama and comedy, but you cannot interpret that first column is drama, second column is comedy, and so forth. Okay, so what are we doing here? We are learning the low level latent factor representation of these users and the items, and we are multiplying them together to get the original preferences. So we are multiplying them together and getting the original references. So when I multiply this U1 with V1, I would get this entry, the rating that user 1 gives to item 1. When I multiply U1 with V2, I would get this entry, right? Did you get my point? So this and this. Okay, take the dot product. Minus 6.3 times minus 0.37 plus minus 0.50 times what is it? 0.94. So you would get minus 0.24. Similarly, you repeat the procedure for the other things. So like this, you will get a matrix of size n by m, where n is the number of items, n is the number of users, m is the number of items, right? So if you see this, it is trying to predict the predicted rating as close as possible to the original rating. So if you see this here, if you see this here, 1 is very much close to the 0.95. 0.95 is the predicted preference and 1 is the actual preference. So wherever the observed entries are present, okay, we would like for example, if you see minus 1, here it is minus 0.81. So our goal is wherever observed entries are present, predict them close to the original preferences, right? So in the process, what are you doing? You're also learning the unobserved entries. So this is unobserved entry. You're predicting as minus 0.24. It means the user may dislike this item. And this is unobserved entry. You're predicting as 0.46. It means user may like the item. So like that, you're also simultaneously predicting for the unobserved entries in that process. Right? So is that clear? Is the procedure clear? I'll tell you how to learn this U and V. But is the concept clear to you? Idea? So this is what. Yeah.
Yes, sir.
Yeah. Thank you. Right. So we are trying to decompose the user item rating matrix into two matrices, U and V, such that when you multiply them, the prediction is equivalent to the actual value on all the observed entries. So this is what your objective is. You want to minimize the difference between the actual value and the predicted value over all the observed entries. So you want to learn U and V. It means what are the parameters of this model? What are you interested to learn?
UV values.
U and V. So the elements of U and V matrices, right? And there are various matrix factorization techniques: singular value decomposition, non-negative matrix factorization, regularized matrix factorization, maximum margin matrix factorization. Depending on the objective function they employ and the constraint they impose, we have got different matrix factorization techniques. We're going to see some of them in this session. So this regularized matrix factorization is one of the simplest formulations of all the matrix factorization techniques. So when you multiply this Uik and Kij transpose, which means this row and this row, you are taking U1 times V1 transpose. Which entry would you get? Which entry would you get? Y11 entry we get, isn't it? This entry would get.
That's
When you multiply U1 with V2 transpose, which entry would you get? Y12 entry you would get, and so on, right? So you're taking that, you're multiplying. So when you're doing this multiplication of U1 times V1 transpose, what are you doing? You're taking U11 times V11 plus U12 times V12. Right, you're doing that, no? So, and taking sum over that. So this is that prediction. And this is the actual value. So this is the actual value and this is the predicted value. You want to minimize the difference, take the squared loss. And this you are doing for all the observed entries. The sigma stands for observed entries. So for all the entries that belongs to this observed entries, you take this mean square error. And this is this regularization term. Fibonacci norm you are taking on U and V. This is very similar to your linear regression formulation. What are you doing there? In the case of linear regression, you're taking yi minus h theta of xi whole square plus theta norm, because theta is the parameter. So here also you're taking this yi minus, this is the prediction, h theta of y is the prediction there, whole square, and these are the parameters that you want to learn, u and v. So therefore take norm on that, okay, to have this regularization term to avoid the overfitting. So this
So
is the
this norm
object.
is for whole matrix or vector, I think. It's
Norm
like
is for,
extension of vectors norm to matrix. Is
yeah,
that?
yeah.
Yes, okay. That confused. Yes. Thank you, sir. Thank you, sir.
No, it is same as that.
Okay.
You're just when you're taking the theta values, what are you taking? The individual values, either you are taking absolute values and summing up, or you're taking squares of them and summing up, and then taking
Yes, sir.
square root of them. Similar way, you do this also. All the individual elements of U and all the individual elements of V, you can
Okay,
uh, take the same way that you do in case of theta.
okay, sir. Okay, sir. Thank you, sir.
So this is to basically avoid the overfitting problem, not to allow them to grow too big. So the same reason here also. So the objective is to learn U and V such that this objective is minimized. Okay. So how do you do that? Based on your knowledge, you tell me whatever that you have learned from last 9 days. Tell me, how do you learn
Either gradient descent or any analytical,
gradient, gradient descent or
any other
analytically?
analytical method or
Yeah, so
Newton's method, anything.
if it is possible, you can do it analytically or else gradient descent
Gradient descent.
approach, right? So the gradient descent approach you can do. How do you do that? You have to learn this U and V. It means that initially you assign some random values to this U and V, then gradually you learn that. You update this U and V values, right? Isn't it? So you initialize these values for U and V matrices randomly, then update them using the gradient descent approach. To update them, find the derivative of J with respect to that particular entry in U or V. Okay, and then you compute the gradient descent. Right? So like this way, so number of approaches can be used to optimize the objective function, gradient descent method and its variables. Start with random U and V and iteratively update U and V. So this is the updation rule. Suppose if you wanna update UIP, which is a particular entry in U, and VJQ, which is a particular entry in V, right? So you can update that using UIPT minus alpha times derivative of J with respect to UIPT. So the C is equal to alpha in our case. So C is some alpha, right? So using the gradient descent algorithm, you can update. And if you compute this derivative of J with respect to UIP, and if you vectorize them, this is how it looks like. Vectorized implementation. It means the whole U matrix can be updated at a shot using this. Similarly, this is the derivative of J with respect to V. Vectorized one implementation of this. It means the whole V matrix can be updated at a shot, not element by element. So this is the vectorized implementation of this. So this you can do it manually also. Like, I mean, the practice that whenever you are trying to derive a new objective function, what you're supposed to do is that you have to first find out the derivative with respect to each and every entry. Once you do that, see how you can vectorize them. Okay, by observing the individual derivations, is there any common pattern based on which you can generalize it like a vectorized notation? So that is the procedure that we follow. But do not take the derivative directly using the vectors. That may not work always. Right? So this is how you can update. And here, this is the cost function. If you observe, when you are computing the cost, you are only considering these observed entries. So this is the indicator variable indicating whether ij is observed entry or not. Okay, if ij is observed entry, then it is 1. If it is ij is unobserved entry, then it is 0. It means it is only considering the observed entries at the time of cost computation. It means you want to minimize the difference between the actual and the predicted only in case of the observed entries. Okay, and simultaneously learning for the unobserved entries. So that's the idea behind this. And non-negative matrix factorization is also same. Instead of this regularization term in case of regularized matrix factorization, we impose another constraint. Constraint is that the entries of U and V shouldn't be negative, right? There should be only positive values. So this is the constraints that we are imposing in case of non-negative matrix factorization, right? So using this constraint, the objective is also same. The rest of the things are same, right? So yeah, so that way you can compute. This is the objective function, and this is the Fibonacci norm of this particular uh, a minus WH. W is equivalent to U, H equal to V, and our notations in the previous slides. This same, only that additional constraint that you are imposing. Similarly, you can represent the matrix factorization. You can give a geometrical interpretation for this matrix factorization. So for some of the matrix factorizations give geometrical interpretation to this U and V. So they interpret the V as the columns of V transpose. It means the rows of V as the items in a n-dimensional space, k-dimensional space. So let's assume n-dimensional space, no problem, right? So like for example, when you're solving for SVM, items are represented in some n-dimensional or d-dimensional space, right? Points in the d-dimensional space, isn't it? So each of the item is described, each of the example or the instance is described with the d attributes or the features. Similarly, V is also representing the items and it has got k dimensions or d dimensions, n dimensions, whatever you call that. Right. So this can be represented as the items in the d-dimensional space, n-dimensional space. And you can plot them. Let's say if the number of dimensions is 2, you can plot all the items, right? So once you plot all the items, you have to learn the preferences, whether the user would like the item or dislike the item. So the user, U, the latent factors of U is represented as a hyperplane that learns the user preferences. For example, this may be a hyperplane corresponding to user 1, this may be a hyperplane corresponding to user 2, and this may be a hyperplane corresponding to user 3. So according to user 1 preference, these are all the items that he likes that are above the plane, and these are all the items that he dislikes that are below the plane. But if you consider user 2, these preferences are changing, right? So though the item representation is same in the n-dimensional space, their hyperplanes may be different. According to their preferences, we learn the corresponding planes. So we represent the items in n-dimensional space, we represent the corresponding U as the rows of U as the hyperplanes that separate positive preferences from the negative preferences. So this is how the matrix factorization gives the geometrical interpretation to this U and V. So based on this geometrical interpretation, there are many methods. One of them we are going to discuss, the very first one, maximum margin matrix factorization. Suppose if you are asked to learn a hyperplane that learns the preferences, which line would you prefer? Right? Which line would you prefer? So this also separating positive with negative. This is also separating positive with negative. Right? So there are many lines possible. Which line would you prefer? The line with maximum margin you would prefer, isn't it? So you are learning the hyperplane that maximizes this width, maximizes the margin. Alright, so remember here in the case of SVM, what is the difference between SVM and this, the concept that I am telling you? In the case of SVM, the points are fixed, x is fixed. Based on x, you will learn a line or a hyperplane. But here, points are also not fixed. You are simultaneously learning them and simultaneously projecting them into a space where you can accurately separate this like versus dislike for all the users and for all the different ratings, right? So this is what the maximum margin matrix factorization is doing. Okay. So when the rating matrix contains only two levels, plus or minus 1, the rows of V can be viewed as the points in the k-dimensional space and the rows of U as the decision hyperplanes in the space separating plus 1 with the minus 1. So you can use smooth hinge loss or hinge loss. Hinge loss is the loss function that we have defined in the SVM. Smooth hinge loss is the updated version of that. I will show you that the smooth hinge loss version of formula. Okay, and the hyperplane act as the maximum margin separators in this case. Okay, so it takes a little time to observe all these concepts. So please be little patient. Right. So this is the objective. So the objective is you're taking, what are you doing basically here is that you may not understand this formulation. Don't worry about that also. So what are we doing here basically is that we are trying to divide this problem of multi-class classification into multiple problems and taking the embedded equation of all these different formulations. So suppose if we get 5 ratings, you are making it into 4 binary class classification problems. So 1 versus 2, 3, 4, 5 ratings. So this is one binary classification problem. That is, when you are taking R equal to 1, you are getting that problem. The corresponding objective you are finding out. And when R equal to 2, you are taking 1, 2 versus 3, 4, 5. Okay, the corresponding objective function or the loss, you are adding it. And when you are taking 1, 3 verse 1, 2, 3 versus 4, 5, when R equal to 3. So that also you are adding. Again 1, 2, 3, 4 versus 5, you are taking, adding all of them to the objective function. So you can imagine that this is one binary classification problem, this is another binary classification, another binary classification, another binary classification. You are adding the loss at this point, loss at this point, loss at this point, loss at this point, and so on. Right? So for that you are using hinge loss. What is hinge loss? If z greater than or equal to 1, if h of z is z in that z greater than 1, then it is 0. Okay, when z greater than, when would be z greater than 1? So this is our, so please pay for attention here. So this is our actual value. Okay, after conversion. So if rating greater than Yij, it is plus 1. Rating greater than less than Yij, then it is minus 1. So in this case, all 1 ratings are minus 1. All 2, 3, 4, 5 ratings are plus 1. Right? So once this is done, so this is our prediction. If prediction is plus 1 and this is our, this is actual value and this is our prediction. Okay, so this is the theta I value you are setting up. If it is positive side of the plane, then this value would be positive. If it is the negative side of the plane, then this value would be negative. So they assume that this is a prediction and this is the actual value. If this is plus 1, this is also plus 1.
இங்க ஒரு CL தான் இருக்கு இங்க CL க்கு 2 இருக்கு
So if this is positive and this is also positive, then what is
CA ஒன்னு தான் இருக்கு CO
Nitya ma'am, please mute yourself.
CL2 மொத்தம் 3 இருக்கு இங்க ஒரு CL இருக்கு இங்க ஒரு CL இல்ல சாரி CL1
Okay, so yeah, if this is positive and this is also positive, what is that means? Prediction is correct or wrong?
Correct.
If the multiplication, if the resultant is positive, then the prediction is correct. So this resultant is greater than or equal to 1. It means that the prediction is correct. So in that case, you are assigning the 0 loss. Okay. If it is in between 0 and 1, it means that the prediction is incorrect, but it is close. So don't assign too much penalty. So you just assign 1 minus z whole square by 2 penalty. If z less than or equal to 0, it means the prediction is correct and the prediction is far away from the actual value. So you assign more penalty of minus z. right? So if z less than 0, say z is -1, of -1, 1 point y penalty you are adding. In the case of hinge loss, what we do is that h of z is equivalent to, which is the SVM, 0 when z greater than or equal to 1, 1 minus z when z less than or equal to 0. Right. So if it is correct, then you are adding 0. If it is wrong, then you are adding more penalty to it. There is nothing else. But here, smooth hinge loss, you are segregating them into different cases and adding penalty according to that. Right. So this is the objective. You are trying to learn these various theta values. It means various lines such that you separate one
Wait.
with Nitya ma'am. Can you please mute yourself? I've muted you, but okay. All right. So if you see this graphically, so this is how it is looking like. So initially, when you randomly initialize, each one of the symbol corresponding to one rating. Okay. So there we have 5 ratings, therefore we have got 5 symbols here. So when I randomly initialize, this is how they look like without any separation. But when you are gradually learning them, so you can see that you will be learning points like this. Okay, so all these 1 rated points are projected to one place, all the 2 rated, 3 ratings, 4 ratings, 5 ratings, and you are also learning the corresponding lines. Okay, right, with separate 1 with 2, 2 with 3, 3 with 4, 4 with 5, and so forth. So these are the threshold values that we are learning. Alright, so this is how this maximum matrix factorization learns multiple lines that separate one rating with the other ratings. Okay, so though it is not fully understood, I hope that you have got at least some idea about this maximum horizon matrix factorization. If you have any queries, you can ask. So we have worked on this problem and we have proposed some extensions of maximum margin matrix factorization. I know it is little difficult to understand at the first glance. So that is why I didn't keep our methods. We have, if you are interested, you can refer to them. Hierarchical matrix factorization using multiple binary triple MFs. This is one paper, and the other one is proximal maximum margin matrix factorization. Okay, so these two papers are the extensions of this maximum margin matrix factorization. We have some improvement over this maximum margin matrix factorization. If you are interested, you can refer to them. But I hope at least it gave you some idea about maximum margin matrix factorization.
Yes.
Any query so
Yes,
far?
sir. Excuse me, sir.
Yeah, Prashant, tell me.
Sir, it is a bit okay, though not completely understood. We got some basic intuition of it. One doubt is that, I mean, it is the number of parameters are here very high. If it is not so, can we use this for multi-class classification instead of neural networks? Because neural networks, we have gone to neural networks because of the complexity of the model. If the complex models are learned here, of course, non-linear models are not learned here. It's separator is more or less linear. Are there any? Is there any
No, no,
non-linear
no.
non-linear
See,
extension?
here it is not fixed. If you
Okay.
see this,
Yes, sir. The
you
boundary
see
is
this,
not
is it
fixed.
linearly separable data? No, right?
No, no.
But gradually you are projecting into a space where it is linearly separable. So you are
Yes, sir.
learning in such a way that it is linearly separable. So the
Yes, sir.
gradually you are projecting them.
Even
Initially it is
points are
not linear.
changed.
Hmm?
Even points are also dynamically
Points
changing.
will also change. Yeah, that's what I'm
Yeah.
telling. There's nothing is fixed based on
Yes, sir.
which you can say that it is linear or non-linear.
Okay, okay.
Yeah,
So, but
because it
then,
is randomly initialized.
Yes, sir.
Points can be anywhere. It's not necessarily linearly. So
Okay.
by default, it is non-linear.
Yes, sir.
But
So one more doubt.
gradually, yeah.
One more doubt, sir. Actually, see here, users and items. You have taken items as a points and users as hyperplanes. Can we exchange both of them? The roles is even then it works. If not so, if we are given things, I mean, what should be chosen as a point vectors and what should be chosen as a
There would
hyperplanes?
be not much difference, I guess.
Okay.
But I mean, what would be the intuition? This is the question. If I
Sir.
have explained the question, I have explained the intuition here now. That you
Yes,
have
sir.
got some points in the space and you have got some preferences, yes or no.
Yes, sir.
So you are using this user hyperplane and separating the positive with the negative and so on.
Okay,
Suppose if
more
you
or less
consider the
class
other way,
labels. Yeah.
what would you explain that you take an item and these are all the users who have rated this item as a positive and these are all the users who have rated this as a negative.
Okay.
Okay. So in that case, how would you classify? I'm just thinking. How would you classify? So you would check with rating. Yeah, it would be more or less same.
More or less. Because we had a item based class earlier, both we have studied correlation as well as cosine similarity. There in cosine similarity, we said it is good for item based similarity. So such kind of analogy do that exist here? So that was my doubt.
I'm just my mind stuck up there only. I have not listened to your question now, but I'm just thinking. So suppose I have explained it very simply for the binary classification that these
Yes.
are all the users who have rated this. Yeah, you can extend it to multiple users also. Like, so these are all the users who have rated this item as one. These are all the users who will rate this item as two, three, four, like that. So yeah, it looks like for me at this stage, it looks like more or less same, except for the interpretation differences.
Yes, sir.
Yeah,
So,
yeah. What is your doubt that you have asked now? I did not
uh,
listen it. Sorry.
yeah, actually, I mean, because earlier I'm unable to recollect the exact word, but we have studied that cosine-based similarity is useful for item-based selection class recommender
Ah.
system, and
Hmm.
correlation is different. I mean, it works for different. So,
Hmm.
I mean, do that kind of analogy exist here also?
Analogy for what?
I mean, here,
In selection of what? There in selection of similarity measure, you are doing that. But in
yes,
selection of what you are asking that analogy here?
here selection of that would you say that the
U
points
and
and
V.
yeah,
U and V.
yeah, yes, sir.
The U
Because
and
we
V
have
are randomly initialized, we are learning them. It's not that the existing points we are selecting. So this
okay,
is a learning process, no? So the
yes, sir.
objective is different. If you take
Yes,
regular matrix factorization, there you are just trying to minimize the difference between the actual and predicted. You are
yes,
considering U and V as the latent factors and multiplying them, and result is the prediction. And you want to
yes,
minimize the difference between the actual and the predicted. That is one
yes,
objective. But if you
yes,
interpret in a geometrically here, like this way, you are
yes,
assuming that the point V is the points and U is the hyperplanes. So
yes,
then you are trying to learn, I mean, you are trying to minimize the objective function such
yes,
that when you learn these points and the lines, the classification is correct.
yes, sir.
Okay.
So,
So in
yes,
both the cases, the intuition, if you see, the
yes,
intuition is same. What is the
yes,
intuition? You want the actual value to be same as the predicted.
yes,
But the interpretation is different.
yeah,
And the objective that they are minimizing is different.
yes, sir.
There we have used square laws. Here we have used hinge laws.
Angels, yes.
Yeah.
So, actually, sorry for many doubts. I
No
mean, I
problem.
am
The
naive.
many doubt means I'll be more happy.
Actually, thing is that here, unlike other the classical, how would you say, loss functions which we have learned earlier, where the loss function is more or less framed uh, to minimize either squared loss or entropy loss or something like that, where we have the predicted y values and our
Yes,
original y
yes.
values and the weights. The loss
Hmm.
function is more or less function of weights. So
Yes.
apart from that, here we have a hierarchy of other variables to define our loss. So my doubt is that can we allow such any other constraint on the loss function according to our new problem, wherein suppose here we have defined new variables to define the loss,
Hmm.
though they are related. Uh, so in that case, suppose if
Yeah,
we
you
have,
can. Here also there are constraints. Constraints
yes,
are the regularization terms.
yes, regularization constraints, and here
Hmm.
we have defined this.
Additional
Uh,
constraints also can be imposed, but
yes,
the consequence of deriving it you need to look at. By imposing those constraints, you will are you putting any is it the derivations possible or not? You have to look at by imposing those
suppose,
constraints.
yeah,
If it
and
is
so
feasible to
yeah,
introduce such constraints without any complications, then you can impose them,
yeah,
provided that you justify that why for
okay.
what you are in using that constraint.
I mean, my doubt was that, I mean, if any the predictor variable, the feature, if can we
Hmm.
use any element within the feature as as a kind of constraint? I mean, that was my doubt, because seeing this way here, by seeing the matrix, I feel that it is related to a kind of feature vector. So can we take any particular point in the feature vector, that column, and can we use that in the loss function? Maybe if it has some more interesting points. uh, I mean, can it be possible, or loss function is restricted only towards parameters and y
No,
values?
no, we are taking column.
Yeah.
See, if you understand it carefully,
Yes, sir.
these columns of V or rows of U are they are the parameters, no?
Yes.
Obviously, you're using them in
Yeah.
the loss function.
Yes, sir. Parameters we are using, sir.
Parameters means the columns of U are V only, no? So
Yeah, yeah, yes,
this
sir.
V is what
Uh,
this is what
which
you're
we
asking. No, we have already used them in the loss function.
Yeah, yes, sir. I mean, not about this in classical loss functions that in general machine learning models, where a squared loss, if we take a squared loss or entropy
Uh-huh.
loss, there,
Mhm.
suppose if we have some kind of here we have Tij. Suppose a kind of constraint is such kind of constraint exists in a logistic loss, for example, where if you want to impose such add some more what do you say, multiply some more factor, an indicator variable, for example, to the entropy loss. Can such be we can
You
we
mean
add
to
that?
ask that can I take this
Yeah.
learned V row columns as the actual features and apply some other model like logistic regression or whatever?
Yeah, yeah, yeah.
That is that what you were asking? Okay. Is
Not
it?
exactly. Yeah, I mean, it can be understood that way, but yeah, I mean, my question is that apart from the existing loss function to the existing loss function, can we add anything from our features? Because maybe some feature is maybe more
You can
demanding of.
add definitely. You can add definitely. You can add.
Yes,
So you can define your loss function
yes, sir.
and you specify the intuition. Like that way only we have got different loss functions. No, if everybody
Yes,
thinks that square loss is the best loss, we will not have multiple loss functions.
yes, sir.
Definitely, you
Yes,
can add my other loss function, but you must have some intuition for it.
yes, sir.
Yeah, to define a loss function. This way, here, what is the intuition? You are penalizing it when it is wrongly classified,
Yes.
not penalizing when it is correctly classified. That intuition is there, no?
Yeah,
And
yes.
so that kind of intuition you should have,
Yeah,
and you should also justify that why do you think that your intuition is better indicated to measure a loss as compared to this loss functions
okay.
depending on the context that may come depending on the context that you are using
Yes.
like for example here hinge loss for a binary classification problem is embedded we are defining an embedded loss function which is for multiple binary classification problems we are not
Yes, sir.
taking these binary classification problems individually like in case of one against all so there we
Yes.
are doing multiple binary classifiers separately we are learning and trying to use them to make the prediction. But here we are
Yes.
not doing that. We are embedding all the loss functions into a single objective, and then we are trying to minimize that objective.
Yes.
Okay, so this is also one way of extending hinge loss to a multi-class problem. Right.
Yes.
So
Yes, sir.
similar way, you can extend the existing loss functions to specific to your domain or a problem or application. Or if you think that these are all the existing loss functions may not work well for a specific application, and therefore it is there is a requirement to have another loss function. And if you could define that, that would be very great.
Yes, sir.
And if
So,
you could prove that that works well.
yes. So this problem, now we can understand this maximum matrix vectorization. It can be an what do you say, a solution for multi-class SVM. We can understand it that way also.
Yeah, yeah,
Yes.
yeah. It is embedded approach for that.
Yeah. Yes.
But
Yes.
there are little alterations required, not
Yes.
exactly. Yeah.
Yes. So one more doubt, sir. In neural network, we have had a dynamic programming solution like backpropagation because of the network relationship between the parameters. Here, because there are large number of parameters, so we have
Because there is a dependency.
dependency.
But here
Here,
we do not have no dependency.
yeah,
Individual
but
entries are
still,
independent of one another.
yeah, we have large number of parameters to learn the whole matrix.
Mhm. But it
Yeah,
is
yeah,
vectorized, no? So,
vectorized. Yeah.
yeah, you can
Okay.
see.
Okay. Okay.
Yeah,
Okay. Thank you, sir. Yeah.
yeah, no problem. So yeah, that's all about the collaborative filtering. Any other doubt you may please ask. Otherwise, we'll take a break of some and come back. Okay. Any queries you can please feel free to ask. Any query? All right. So take a break of 15 minutes. Come back by 6:45. So I'm giving 15 minutes break. I assume that your brains are overheated. So please take a break of 15 minutes and come back by 6:45. Thank you. So welcome back. Shall we start?
Yes, sir.
Thank you. So far we have seen one paradigm, collaborative filtering based techniques. Then the content based is recommender systems, we'll see. So it is based on your past preferences. It will recommend the similar items to you. Suppose if you have comedy movies, then comedy movies. If you have liked drama movies, then it will recommend drama movies. If you have liked action movies, then action movies, something like that. Okay, so here we give the user preferences as input to the model and item descriptions also. So this is very important. In case of collaborative filtering, we do not require any item descriptions. We just need the community data. Whereas here, the item description is required. Okay, what features are present in the item. So the characteristics of the item are important here. So it recommends the item similar to what the user have liked in the past, so instead of what similar users like. So that's the difference between the collaborative filtering and content-based filtering. Okay, so for example, each item or a book can be represented with some set of characteristics like genre, author, type, price, keywords, and so on. So this defines the attributes, right? And user profile also have some attributes, so explicitly specified by the user or automatically learned by the user. So this is the user profile in which we have the keywords like detective, murder, new act. So see which of these books intersects with these keywords more. Okay, the similarity between the keywords can be learned. Right? So compute the similarity of the unseen item with the user profile based on the keyword overlap. If they are highly overlapping, it means it is highly similar. If it is less overlap, then it is less similar to the item. Okay, so there are some measures of similarity, Jacob coefficient or Dice coefficient, which measures the similarity in terms of the intersection between the two sets. Okay, so one set is the user profile, the other set is the candidate item. So you make this similarity for all the candidate items that are unseen by the user and make the recommendation according to their similarity values. If it is highly similar, then you make the recommendation. But the problem with this is that some longer documents maybe automatically overlap, maybe it is highly overlap to the user profile, because longer words there is a possibility of all the keywords, then there will be a high overlap to the user profile. So in that case, what would happen? You may always tend to recommend the longer documents to the user. Okay, so that is why there is another measure to measure the similarity between the two documents or two sets of keywords. Okay, so that is term frequency and inverse document frequency. So this you might have already heard, right? So the intuition is that if a word is frequently appearing in the document, then that word must be an important word. Okay, so we should give that word a high score. Okay, and on the other hand, if the word is appearing in too many documents, okay, so there may be a word, it's not, we usually remove that word, stop words, but I'm just giving you some example. There may be a word which is appearing in all the documents, right? So then probably that may not be a unique identifier. So therefore, we should assign a low score to that word. Okay, so if a word frequently appearing in the document, you have to assign a high score, and that is term frequency we call it as. If a word which is appearing in all the documents, I mean more number of documents, then we should reduce the importance of that word. Okay, that we call as the inverse document frequency. Okay, term frequency, the number of times the word has appeared in the document, and inverse documentary frequency is reduction of the importance of a word which is appearing in all the documents, right? So this is term frequency, which is term frequency, number of occurrences of a word in the document, dj, n dj's, right? And this is inverse document frequency, which gets low if the word is belong to so many number of documents. Like for example here, if you compute the term frequency is 2 by 4 for a word rock and for the document d1. Okay, so the rock is appearing in 2 words and total number of words in that document are 4. So 2 by 4 is the term frequency. And inverse document frequency, if you see, this word rock is appearing in 4 documents and the total number of documents are 6. Okay, so if this gets high, if the denominator gets high, and this total value will decrease, right? If this gets low, if the denominator gets low, then this will be higher. So if the document is appearing in all the, sorry, if the word is appearing in all the documents, then you give lower importance to that. So right, so you multiply term frequency and inverse document frequency, you would get term frequency TF-IDF measure, right? So you measure the TF-IDF measure and make the recommendation accordingly. Right, so there are some improvements to this vector space model, like remove the stop words which appear in nearly all the documents, stop words like the, a, and, on, something like that. Use stemming and replace all the words with that stem, like stemming, stem, stemmed, all these words can be replaced with a single word stem, right? And size cutoffs, you just pick up the top and most relevant words instead of using all the words to and make the vector very sparse, right? And you can use the lexical knowledge, use more elaborate methods for feature selection, like remove words that are not relevant in the domain. And you can also detect the phases as terms, like United Nations can be detected as one. This is one phase, you can detect that as a single term instead of making United and Nations 2 terms. Okay, and there are some limitations of this. Limitations are the semantic meaning remains unknown. Like for example, if there is somebody who is saying that there is nothing good for vegetarians in this restaurant, if somebody say given a comment at the time of giving rating that there is nothing good for the vegetarians. Okay, so maybe when somebody is searching, the word vegetarian may be given high importance, and when somebody is searching for the vegetarian restaurants. Okay, so that way semantic meaning remains unknown in case of this content-based recommender systems. Right. So once you get this, you can make recommend items based on the, once you get the this term frequency of these words and the documents. This is like a feature. You can consider this TF-IDF values as the features, and you can apply nearest neighbors algorithm or any of the decision trees, wherever the classification algorithm you can apply and make the recommendation or make the prediction, right? So that is how you can do this content-based recommender systems. So once you represent this vector, I mean TF-IDF vector, that is a feature vector. Now you have got feature vector and the corresponding rating given by the user. Feature vector is this TF-IDF vector and the corresponding rating given by the user, right? So once you get the data in that format, right? So you have got item 1, so for that TF-IDF vector and the rating given by user. Item 2, TF-IDF vector, rating given by the user. So once you get this in this format, given a new item, IN plus 1, for which you know the TF-IDF, and you have to classify. This is document 1, document 2, so on. Document N, we have given information, but N plus 1, we don't have this information. You have to classify that. So dn plus 1, you compute this TF-IDF vector, and how can you do that? You can use any of the classification techniques, right, to make this prediction. So that's what it is basically saying. You can use any of the linear classifiers, decision trees, SVMs, any of the classifiers, nearest neighbors, right? Once you get the data in that format. Alright. So is that clear?
Yes, sir.
Yeah. So so content-based recommendation advantages, if you see, there is no cold start problem because we are not depending on any other user rating. Okay. So even if so there is no cold start problem. User independence is there, does not depend on any other users. And new items can be easily incorporated. So no cold start problem. And there is transparency is there. Explanations can be given. Why is it recommended? Because it is similar to the items that you have liked in the past. So that explanation can be given. And it is easily understandable. And by the way, there is something called justifiable recommender systems, in which we give explanation why we have recommended certain item to the user. Like those who have bought also bought this. That is why we are recommending. So this is explanation that we are giving. Because those who have liked this item also like this item. So this kind of explanation we give. That is justifiable recommender system. Limitations are this: limited content analysis. Content may not be automatically extractable, and missing domain knowledge in some cases, and keywords may not be sufficient sometimes. And the main problem with this is over specialization. It may tend to recommend more similar items, too much similar items, more of the same. Okay, so that is over specialization problem is there with content based. And another problem is how to make recommendation to the new user, because rating or any information about the user has not collected yet. So how can we make recommendation to this new user? That is also a problem. The next one is knowledge-based recommender systems. Knowledge-based recommender systems. So can anyone tell me what knowledge-based recommender system, based on what it recommends? Based on the user needs, isn't it? Recommend me that suits for my needs, right? Why we require this knowledge-based recommender system? So it is more or like tell me what fits based on my needs. Knowledge models are required for this. Knowledge models are that knowledge about the user requirements or user needs, right? So why do we need this knowledge-based recommender system? Because products with low number of available ratings. So the collaborative filtering technique works based on the ratings, and in general, we consume the items, but we don't rate the items. Okay, so this may happen with any one of you also, even if it happens with me. I order the items, but I never rate the item. Okay, so products with very low number of available ratings. And the time span plays an important role. For example, your requirements 5 years back may be different from your requirements now. 5 years back, your family situation may be different from your family situation now. Okay, so therefore, your requirements may be changing. 5 years back, your requirement may be 4-seater car. Now your requirement may be 7-seater car. Okay, so and 5 years back, computer ratings doesn't make any sense now, right? 5 years back, 8 GB means it's a very good system, but now if you see 8 GB, it is very normal, right? So the time plays a crucial role here, right? And customer want to define their requirements explicitly. Like you may require 7-seater car, you may require black car. The color of the car should be black. Okay. So user want to specify their requirements explicitly. So due to all these reasons, knowledge-based recommender systems are required. Okay. So there are two main types of knowledge-based recommender systems: constraint-based, case-based. Constraint-based, based on the explicitly defined set of recommendation rules, we recommend the user. We want to match these requirements of the user with some item. Okay, so that fulfills this recommendation rules or the constraints given by the user. Okay, you may define some constraints like color should be black, color of the car should be black, it should be a 7-seater car, there should be 4 airbags. Okay, price should be less than 10 lakh. There may be all these requirements that the user specify. Okay, so according to the constraints specified by the user, we try to map this to the cars available and we shortlist and present to him. based on the different types of similarity measure. So they may not be any car exactly that suits to the user requirement, but there may be a similar car. Okay, so they may not be 10 lakh the car within less than 10 lakh within that specification, but there may be a 11 lakh car. So similar. So there may not be a black color car, but close color may be there. So it measures some similarity between the constraint specified by the user or the requirement specified by the user and the actual values or the attributes of the object. Right? And both approaches are similar in their conversational recommendation process. What is conversational recommendation process? Users specify the requirement, system try to identify the solutions. If no solution can be found, user change the requirement. It is a conversational recommendation process. Like for example, you may specify when you are purchasing shoes. Okay, you may specify some requirement and makes the recommendations to you. Okay, when it makes the recommendations, one of the item may be looking close to you, close to your requirement, and you may select a particular shoe and say that this is fine, but it is better if I have high heels than this. Heel should be a little larger than the whatever that I have selected the image. Okay, it may be again shortlisting some items and presenting something to you. And when it presents something, some set of items to you, you may select one item and say that this is fine for me, but if it is good, if I have a shiner shoes than this, right? So what is that you are doing? Iteratively, you are defining your requirements to the system, and it is making finer and finer recommendations to you. Okay, in an iterative process, right? This is a conversational recommendation process. Okay, and constraint based recommendation, this can be formulated as a constraint based recommendation problem. You select items from the catalog that matches the user's requirement. Suppose you want to purchase a camera, and these are all the features that defines the camera. P1 to P8 are the cameras, and these are all the features that defines the camera. Price of the camera, megapixels of the camera, optical zoom, LCD size, movies, sound, waterproof. All these are the features of the camera, right? So user requirement can be, for example, the price should be lower than 300 euros, or the camera should be suited for sports photography. These are the requirements of the user. Okay, so the user specifies his or her initial preferences all at once or incrementally in a wizard style, right? Or in an interactive dialogue mode. So whatever the user specifies is her initial preferences, and the user is presented with some set of matching items according to his requirements or the preferences, with an explanation as to why a certain item was recommended. And the user might revise his or her preferences. Then we look for the alternative solutions and narrow down the number of matching items. So as you go level by level, the finer and finer recommendations we are making to the user in an iterative process. Okay, if no solution can be found, then in the case of unsatisfied requirements, if you are not finding any solution to the user, constraints can be relaxed. Okay, so you can ask the user to relax the constraint. So goal is to identify the relaxation to the original set of the constraints. Okay, and user could also be interested in repairing proposals, right? So recommended can calculate a solution by adapting the proposed requirements or the revised requirements. Okay, so this is how you can. Okay, I think I missed some slide. Give me a second. Sorry for this. Actually, I thought of checking it one more time. What happened was I made some changes and closed it when I asked that do you want to save? I clicked on don't save by mistake. Okay, so some of the things were missed. Give me 2 minutes. Sorry for the inconvenience. So ranking the items. We use the multi-attribute utility theory here. Am I audible?
Sir, you are audible.
Yes, sir.
Okay. Yeah. So, for example, the quality and economy are the dimensions in the domain of digital cameras, based on which you would like to judge. Okay. And if this is how we have defined the quality and economy according to the attributes. If the price less than $250, then the quality is 5, economy is 10. If the price greater than $250, then quality 10, economy 5. And a megapixel is less than or equal to 8, then quality 4, economy 10. Like this, we have defined this by with the help of the domain experts. Okay, so please take the photograph of this one. So because we'll solve this problem. Please take a photograph of this. Shall I move to the next slide? Have you taken?
Yes, sir.
Yeah.
Sir, wait, sir.
Yeah. Okay.
Okay, sir.
Yeah, sure. So this is how we have defined. Please take this also. Photograph of this also. So the price less than 250, quality is fine. Like that, the quality and economy parameters are defined by the domain experts. Okay. So now, suppose if I have a user who is giving more importance to the quality than economy, then I may have a different set of recommendations to him. Suppose if I have a user who is giving more importance to the economy than quality, then I may have a different set of recommendations to him. Okay, so this is the data that I have, and these are the parameters that are defined by the domain experts. Now I have got the user requirements. So these are the user requirements. I've got two customers. Customer one preference is that he is giving more importance to the quality than economy. So he is more inclined to the quality. His 80% preference is quality, 20% is economy. Customer two, who is more inclined to economy than quality. 40% quality and 60% economy. Okay, so now tell me, according to this parameter quality, what should be the value of how many attributes we have got, by the way? Can you look at the photograph and tell me how many attributes? How many attributes? 1, 2, 3,
7, sir.
4, 5, 6, 7. 7 attributes, right? So according to the quality attribute, what should be the value of uh, camera on a feature 1? What is feature 1? Feature 1 is 148. Is it less than 250 or greater than 250? Less than 250. If less than 250, what should be the quality parameter? 5 or 10?
5.
5. So I give 5 here. So this 5 came from that. Okay. So next parameter is what? Next parameter is MPix. Okay. MPix, the rules are, if MPix less than or equal to 8, then it is 4. Otherwise it is 10. So what should be the value for camera 1 for this on quality parameter? Should be 4 or 10?
4.
4.
It should be 4.
4.
And simultaneously look for the economy parameters also. Economy is 10, right? Quality is 4, economy is 10. 4, 10, right? So economy is 10, this one, right? So what is the third parameter? Third parameter is optical zoom. And what is the rule here? Optical zoom less than 9, then it is 6, otherwise it is 9. So what is that value for first camera? Less 4 times, right? Which
6.
is less than 9. So it should be 6. So this is 6 and this is 9. Okay. So like that, You evaluate each of this camera on the basis of quality and economy and define the corresponding parameters and take sum over that. Okay, so the quality value is 41 for the camera 1 and economy is 65. Similarly, you estimate the quality value for camera 2 and quality and economy values for camera 2, camera 3 and so on, camera 8. Okay, so now customer 1 who has got 80% preference to the quality and 20% to the economy. Okay, so what should be the score for camera 1? We should give more weightage to the quality, right? It means 0.8 times quality parameter, which is 41 plus 0.2 times 65, right? This is equivalent to 45.8. 45.8, right? So I've got this value 45.8. And similarly, can you tell the same for customer 2? Customer 2 who have got 40% to the quality and 60% to the economy. Can you tell me how would you compute the score of camera 1 for customer 2?
0.4 into 49.
4 into 40.
9.
I'm asking for the camera 1 only. Camera
Okay.
1.
41.
41 plus
0.6 into 65.
0.6 into 65, and this is equivalent to 55.4. Okay, so now can you tell me the same for customer camera 2 with respect to customer 1 and customer 2? Camera 2,
0.8
customer
into
1 first.
40. 0.8 into
0.8
49.
Plus,
Plus 0.2 into 64.
so this would be equivalent to 52. And customer 2,
0.4 into 49.
0.4 into 49 plus
0.6
into
into
64.
64. So this is equivalent to 58. So the same way you compute it for all the cameras. Once you get the score for all the cameras according to the preferences, then you rank them. Okay, so you can see that 63.8 is the highest score. So you rank it as a 1. Next highest score is 60.4. You rank it as 2. Next highest is 57.4. You rank it as 3 and so on. And recommend top key items to the user. Similarly, here 58 is the highest score. You rank it as 1. 57.8 is the next highest. Rank it as 2 and so forth. Okay, so this is how you can compute the scores using the multi-attribute utility, multi-rank, right? So any query here, I'll take. Any
Not
queries?
not queries, just clarity. I mean, here we have a database of cameras or users that cameras only.
Database of cameras
Yeah.
and the user's preferences.
Yes.
Preferences means the knowledge model. How much
Yes.
preference I give for quality, how much preference I give for economy, which is defined in the knowledge model. So the
Yes.
knowledge model also the input and the database of objects also the input.
Okay.
And in between whatever that we have got now, this one, this
Yes.
is from the domain experts. So you
Okay.
need domain experts to define this quality and economy parameters.
Yes, sir. Yes, got this. Thank you, sir.
Right. So items are retrieved using the similarity measure in the case-based recommender systems. You can measure the similarity between the item and the user preferences multiplied by the weightage that you give to the corresponding requirement. So all the requirements may not be of equal weightage. Okay. Maybe my high weightage to the 7-seater car, not the color of the car. Okay, so you make the similarity accordingly based on the weightage that you give to a particular feature and find out the similarity and recommend the similarity items with the highest similarity. So the summary is that knowledge-based recommender systems can be either constraint-based or case-based. In the iterative
Uncle
process,
Namaste.
both are same. Both are same.
వచ్చేటట్లేదు.
Right. So the limitations of this are cost of the knowledge acquisition is more. Like, because from the domain experts you have to acquire some knowledge, from the users you have to acquire some knowledge, from the resources you have to acquire some knowledge. All these are the costly operations. And accuracy of the preference models, to get a very fine granular preference model, you may require many iterations, which is also a time taking process. And whereas if you take collaborative filtering models, the preferences, they implicitly define the preferences and automatically learn the preferences. You need not ask the user explicitly. And the independence assumptions can be challenged. Like, for example, preferences are not always independent from each other. Right, so that's all about the three null paradigms that we have discussed so far: collaborative filtering, content-based, then knowledge-based. Hybrid recommendation is combination of various techniques or the collaboration of various data resources. Right. So hybrid is a combination of various inputs and a composition of different mechanisms. Right, like collaborative or content based, knowledge based, you can combine them in different ways and see, get the hybrid recognition. So there are different hybridization designs. These are the three most popular hybridization designs: parallel use of several systems, monolithic exploitation of different features, behind the different designs. Okay, so in this way, hybridization is virtual because the features and knowledge sources are different paradigms are combined. Okay, you're combining the features of different recommender systems, strategy 1, strategy 2, all that you are implementing in a single system. Okay, so this is one way. Only a single recommender component is here, which is a hybrid recommender component. Monolithic hybridization design, we call this. The next one is parallelized hybridization design. Here, output of several existing implementations are combined. Okay, so recommenders, we give the input to the different recommender systems, and we have a explicit hybridization step which combines the output from the multiple recommender systems. Like, for example, it may say that the items that are common to the all recommendation sets is the final recommendation, or it may take the scores and merge the scores. Okay, or it may merge the recommendation. So like that, it may follow the different strategies at the hybridization step. Okay, and what weightage that you give to these individual recommender systems can be learned automatically, dynamically. Okay, and you can give equal weightage also sometimes. So
Like ensemble.
yeah.
Yeah.
Sorry, Prashant?
Like ensemble learning.
Yeah.
Yes, thank you, sir. Yeah.
And the other one is pipeline hybridization design. It means the output of the recommender system 1 given to the recommender system 2. Right? It means that every recommender system, what are you doing is that you are selecting, you are making a finer and finer recommendations. So at the first step, you may recommend 100 items. Out of that, you're giving it to the second recommender system and filtering it further, giving 50 to the third recommender systems, filtering it further and giving it to the third. It's not necessarily reducing the recommender system always, but the idea is that each and every recommender systems, you are improvising it and making it more finer recommendations to the user at the next level. Okay, so this is the idea behind the pipeline hybridization design. So you can follow any of these designs, and there are other designs also. You can follow any of them. The idea is that you combine multiple methods. Yes, Rashmi. So the next thing is evaluating the recommender systems. So now the question is, we make the recommendation using any of these design techniques, paradigms that we have discussed so far: content-based, collaborative, knowledge-based, hybrid, whatever. Right? Now, how do you judge the performance of a recommender system? How do you assess the performance of a model? How can you say that the recommendation that you made is correct? Okay, so there must be some evaluation measures for that, right? There are lots of measures. I'm not going to discuss all of them. The most common methods I'm going to discuss. Right. So we establish, so ground truth is established by the human experts, like what is actually good, actually bad, is established by the human domain experts or by the user. Okay, and this is the prediction which is rated good, rated bad. If the rating is, I mean, prediction is rated good, actually also it is good, then it is comes under true positive. If the prediction is good, but actually it is bad, then it comes under false positive. It means it is falsely predicted as positive. Falsely predicted as positive case. Similarly, false negative is falsely predicted as negative case. It means actually it is good, but your system giving it as bad. Okay, it means it is falsely predicted as negative. We call it as a false negative. So the confusion comes usually between false positive and false negative. That is why I am telling false positive means falsely predicted as positive. False negative means falsely predicted as negative. So there no confusion then, right? So if the rating is good, I mean prediction is good, actually is bad, then false positive. If the prediction is bad, really it is good, then it is false negative. And the true negative is actually it is bad, prediction is also bad, then it is true negative, truly predicted as negative. True positive means truly predicted as positive, right? So these are the different values that we are getting, from which we can compute our evaluation measures. So we can get precision. Right. So these are all the recommended items, prediction items, and these are all good items. Okay. So whether there is an intersection between them or not. What is recommended is what is good or not. Okay. You can compute the precision by true positive divided by true positive plus false positive. It means good move is recommended divided by all recommendations. So you can also write it as recommended intersection interested divided by the total recommendations. Recommended intersection interested divided by total number of recommendations. Okay, so this is recommended intersection in interested is true positive, and total number of recommendations is true positive plus false positive. Right? And recall is the same thing in the numerator, recommended intersection interested divided by all interested movies by the user, all good movies, all the movies liked by the user in the test set. So this is good or bad, we decide based on the test set. In the test set, if he has given more rating, then we say that it is good. If in the test set, if he has given low rating, then we say that it is bad. Okay. And if you plot the precision versus recall, we call this as the area under curve. It should be towards the right top corner. It should be something like this. Okay. So the more it is coming this side, it is less efficient. The more it is coming this side, then it is efficient. So the area under curve must be high. Okay. The precision also should be high. Recall also should be high. Right? If it is high, then it is a good recommender system. Otherwise, it is not. Then F1 metric is another metric which is 2 times precision times recall divided by precision plus recall. This is also one of the standard metrics to evaluate the recommender systems. And if it is a rating prediction systems, then you can evaluate MAE, which is the mean absolute error. You can also evaluate root mean square error, which is the square root of the individual items error squares. Error is the difference between the predicted and the actual. Okay, so root mean square all of you know, so no need to explain much. And there are some evaluation measures based on the ranking like NDCG, DCG. There are various measures based on the ranking also that are not kept in the slides. But yeah, these are the different evaluation measures. Thank you very much. Happy learning. And if you have any queries, I'll take. Otherwise, we'll proceed to the implementation part.
Sir, excuse me, sir. So,
Yeah, Prashant.
this more or less recommender system seems to be a classification technique because there we have some kind of
Classification or
classification
ranking problem.
ranking problem. Yeah, because we have the labels more or less.
Yes.
Yes, sir. In case of clustering, how we decide whether cluster, what are the metrics for evaluation of clusters? Because we don't know the class levels. So how can we
Uh,
evaluate that?
So there are, suppose if you have a labeled data, I mean, usually for the testing purpose, we take the labeled data, but we
Yes.
don't use the labels.
Okay.
Okay, we don't use the labels at the time of clustering, but at the time of evaluation, we use the labels and see whether all the data points that belong to one cluster or belong to one class or not. This is one way that you can evaluate at the time of testing. And another way is that if you do not have that label information at all, okay,
Yes.
I mean, suppose if you want to evaluate on the data set where you don't have the label, then
Okay.
that intra-cluster distance, inter-cluster distance you measure, and there are some other measures also which is based on purely based on the distances.
Okay.
Yeah.
Okay. Sir. Thank you, sir. Thank you, sir.
Yeah, yeah. So any other query? All right. Pramod sir will not have a class tomorrow. This is the last day. So the recommender systems can be implemented using a surprise library, scikit surprise library. This you need to install if you are doing it in your local system. If you are directly doing it in Google Colab, you need not install. I have already shared that in your Google Drive. You can just install it. So, but in the surprise library, there are very few recommender systems, SVD, KNN, Basic, non-negative matrix factorization, NMF. Very few recommender systems are there, but it is very easy to implement using this library. So I have also imported the data set from the Surprise. So this has some standard data sets in the Surprise library. As I've told you, MovieLens is one of the standard benchmark data set. In MovieLens itself, there are many data sets. MovieLens 100K, MovieLens 1 million, MovieLens 10 million, MovieLens 20 million, MovieLens latest, MovieLens 30 million, like that. There are many data sets. So out of that, I've loaded MovieLens 100K data set, which was the very first data set from the MovieLens. Right, so load built-in data set, which is MovieLens 100K. I've loaded it, which is in the data, and algorithm I'm calling is NMF. Okay, so like the similar way, you can call any of the recommender systems that are implemented in the surprise library. Okay, and then I'm calling cross validate. So if you have no idea about cross validation, cross validation is kind of dividing the data into multiple folds. Let me open this for better explanation. So suppose usually what are we doing in the case of when at the time of testing, we are randomly dividing the data into training and testing, right? And we are training our model on the training data and testing with respect to the test data. But because this randomly selecting training and testing, maybe your model biased to a particular division. Okay, so to avoid that, we do k-fold cross validation. What we do is that we divide the data into k-folds. Suppose if I say 5 folds, I divide the whole data set into 5 folds. 1, 2, 3, 4, 5. The whole data is divided into 5 different sets randomly, subsets randomly. At each time, I'll take one of the fold as the testing data and remaining folds as the training data. Right. So for example, if I take 5-fold cross validation, I divide the data into 5 folds. So at the first iteration, at the first run, I take first fold as the test, remaining fold as the training. At the run 2, I'll take second fold as the test, remaining fold as the training. And so on. I repeat it for the 5 times and I cover all the instances in the test set. And each time I measure the MAE or whatever the measure that I have selected in each of these folds. So suppose if the measure is MAE, I take MAE at run 1, which is MAE 1, MAE at run 2, which is MAE 2, MAE at run 3, and so on. I get 5 MAEs. I take the average as the final MAE. So this is 5-fold cross-validation. To do this k-fold cross-validation, you have a method in the Python, which is cross-validate, which you can import from surprise.model selection. You think it is there in the SQL learn also, SQL learn.model selection also, you can import cross-validation. So cross-validate, you need to pass algorithm, okay, the base algorithm based on which you want to do the cross-validation, and the data that you need to pass to this algorithm, and measures, what kind of measures that you want to measure, evaluation measures. So I passed 2 measures, MASE and RMS. MAE mean absolute error, RMSE root mean square error, right? And CV equal to 5, which means that cross validation is 5, right? So these are the different important things that I am passing. Verbose equal to true, I think I forgot this actually, but this is also something related to the selection. Okay, so please do explore. I forgot that option. I remember till the beginning of the session, but now I couldn't recollect. Okay, so sorry for that, but please, yeah. So please explore that. No problem. So you cross validate. Now you will get MAE and RMSE like this. At fold 1, this is MAE, this is RMSE. And at the time of training, this is the error. At the time of testing, this is the error. Okay. Sorry, fit time, it means training time. This is the training time, this is the test time. Okay. So this is the information or the scores related to fold 1, fold 2, fold 3, fold 4, fold 5. And if you take the average, which is the mean value is this, mean RMSE is this, mean MAE is this, mean execution time for training is 4.56, mean testing time is 0.13, and this is the standard deviation. Okay, how much it is deviating in each and every fold. Okay, so this is how you can measure. Similarly, you can take another recommender system like SVD. You can take KNN basic. Whatever the recommender system that you take, you define the corresponding options and pass that algorithm to the cross validate and data to the cross validate and the measure to that. Okay, so right, is that clear? Any doubt here?
No, sir.
Okay, cool. Then matrix factorization, let us try to implement it from scratch. Matrix factorization from scratch. Okay, so this is the code credit goes to Dr. Vikas Kumar. He is my friend. He works in University of Delhi. Okay. So these are the libraries that we are importing libraries. Different libraries that are required, pandas, numpy, matplotlib, right? And this is the MAE error that I am defining, which is the absolute difference between the true rating and the actual rating for all the instances where the observed entry are present. If the actual is not equal to 0, then only you are doing this, right? And taking the average, right? And returning that score. Similarly, the same thing that you are doing for root mean square error, right? Squared error, sum of the squared errors you are taking and root mean square of that you are computing. So to compute square from the NumPy library, you are using scale, right? And this is a test train split. Tested train split, how are we doing is that for each of the users, the number of test instances are defined. So that place, like for example, 30% of the rated items or the observed items is the test set. Okay, for each and every user we do this. Okay, so what are we doing? we are taking the observed entries for all the users, observed indices for each and every user. So user in the range of ratings dot shape of 0. So rating dot shape of 0 means number of rows in the ratings information. Number of rows equivalent to number of users. Okay. So for each user, we are getting the non-zero entries. Non-zero entries are the observed indices. Once we get them, we are taking a choice of number of test instances or total number of object, whichever is minimum. Okay, so we are selecting those many number of instances. Replace equivalent to false means this is random sampling with replacement or without replacement. If you specify replacement equal to false, which is random sampling without replacement. If you specify replace equal to true means random sampling with replacement. So we don't want to take the duplicate elements in the test. That is why replace equivalent to false. Right. So you are dividing the training and testing. So all these test ratings that you have picked up, you are making them 0 in the training data, and you are just picking up those rating indices that you have picked up in the test set and making that as a test set. So you have divided the data into training and testing. Okay, so ensuring that these two are disjoint, training data and testing data are disjoint. Right, so this is the train test split that we are doing here basically. Then comes the matrix factorization, in which we are passing rating matrix train data, U, V, which are the parameters that we need to learn, and K, which is the latent factor. Okay, what should be the size of the latent factors? You have to divide the data into n by k times k by m, right? So what is that k? Okay, and number of steps, number of iterations that you want to repeat, learning rate alpha, and lambda, which is the weightage that you give to the regularization parameter. Okay, so these are the parameters that you are passing to this, and this deciding this alpha is 0.005 is based on after training it for number of different number of alpha values. It means after hyperparameter tuning, he has fixed it to alpha equal to 0.0005, lambda equal to 5. Okay, so this is after tuning the parameters. And the termination criteria that he has chosen is if the value is increasing, like it looks something like this, no? Your curve looks something like this, right? If it is increasing, then stop, but don't decide based on one iteration increase. You look for some number of iterations, 5 number of, you maximum allow the count, let's say 5 or 6, whatever. So if it is increasing after those many number of times, you stop the algorithm. Okay. So maximum increase allowed is 5, and you are initializing count to 1 by 5 to count these increases. Okay, how many number of times it is increased. Okay, and this is the R approximation. It means the predicted value for the rating, which is the dot product of U and V transpose. That's what we have seen, right? U times V transpose is equivalent to R prediction. So this is R approximation, which is the dot product of U and V dash, V transpose. Okay, where U and V are randomly initialized initially. Okay, and now we compute the error. Error is the difference between the training data and predicted data. R train minus R approximation, and this you are only considering the entries where R train is not equal to 0. It means only considering the observed entries. So once you get this error, you compute the objective function, mean square error, which is E square. Error square, right? Mean square error is difference between actual and predicted whole square. So you are taking E square and lambda by 2 times power of U comma 2, which is the regularization term. This is the regularization term on U, and this is the regularization term on V. Okay, so this is our objective. This is an error term. This is the regularization term. Okay, so this is the objective value that you are getting, which you are referring it as old objective, because you're going to update U and V values and compute the new objective. So you are repeating this for number of iterations as specified number of steps, right? So which is 1000 number of times you are repeating this. So in this you are computing the derivative of U with derivative of j with respect to u, which is you're referring it as du. This I have given in the slides also, right? This equation I have given in the slides. We are implementing the same equation, which is the derivative of j with respect to u, and this is the derivative of j with respect to v. After getting that, what is the updation rule? U equal to u minus alpha times derivative of u, derivative with respect to u, v equal to v minus the alpha times derivative of j with respect to v. But you're not directly updating, you are storing them in some temporary value. Okay, the reason will be explained in later. Right, so using this new values, you are computing this again approximation or approximation, again computing the error, and this is new objective. After updation, you are computing this objective. I'm just printing this objective to see whether it is increasing or decreasing, but if I print at each and every iteration, it may look clumsy. That is why for every 100 iterations, I am printing this objective function, right? So, and here, if the old objective less than new objective, it means what? It is increasing. Objective is increasing in slope. Then you count it. Okay. So if the count is equal to maximum increase allowed, then you break the loop. You will terminate it. So that this is the termination condition that I am defining. Otherwise, you make this u to u temp, v to v temp, and old objective to new objective, and repeat the procedure. And append these objective values to this old objective to objective values, because you want to monitor this objective values. So you are returning finally u, optimal u and v, and this objective values over the number of iterations. So this is a simple matrix factorization technique. Very simple, right? You are in randomly initializing u and v. Random initialization will be done before calling this matrix factorization. Once you receive this random initialized u and v, you are computing the objective, updating the u and v values over the number of iterations, and stopping based on the termination criteria. So very simple, right? So now start using this matrix factorization that you have implemented here. So this is the rating path. So this is, I have this data set in my folder. You can download it from MovieLens 100K. If you type, you will get the data set easily, very easily. You can download it and place, no problem. Otherwise, I can also give, I can keep in the folder. For now, I didn't keep. I'll keep it after this session. Okay, so date 10. So this is the data set ML 100K. So in this, ratings are like this. Right, this is the user ID, this is the movie ID, and this is the rating given by this user for this movie, and for this is the rating. 3 has given, 196 user has given 3 rating for movie ID 242, and this is the timestamp when he gave that. Okay, we don't need this information for this matrix factorization. If you are working with some sequence data, then that information is written. Yeah, so this is user ID, movie ID, and rating. Okay, so this is how the data looks like. And the next one is movies. So these are the movies. Okay, movie toy data. Actually, this actual data set is different. I think he has changed it. Let me show you that actually. This is how the actual data looks like. You just copied the first 2 columns. So these are the different genre. Action is present or not. Adventure is present or not. Animation is present or not. Okay, so this is another feature. Children's, it is applicable for children. Children can see it or not. Comedy movie, crime or not. So these are the different genres of the movie. This is how the data looks like. But we want just these titles and movie IDs. That is why he has taken that the other data set, right? So like this, right? So we have both the rating path and movie path. So I'm reading them. Okay, so read CSV rating path. So this is the rating information I've got. Read CSV movie path. This is the movies information I have got. Okay, and ratings dot pivot of index of user ID, column ID, values rating. It means what? You're passing this triple column data, no? You have got triple column data. user ID, movie ID, and rating. To convert this into a matrix format. Okay, so you are defining what is the your row index, what is the column index, and what should be the entry. Okay, so these are the three fields that you are passing to that function. So if you see this is the index, which means that row ID you are passing, which is user ID, column ID is movie ID, and value is rating. So these three columns you are defining, this will return the rating matrix. Okay, and wherever the entries are not present, you are making them zeros. Okay, so wherever NA is present, you are making them zeros. So once you get this rating matrix, you are converting that into a NumPy matrix, NumPy array, right? So and then taking length of R as number of users, length of R0 as the number of columns, right? Then which is M, number of movies and number of features you are taking, and number of users, number of movies you are taking, and this is the number of features that you are initializing. Number of latent factors you are deciding, which is usually less than minimum of M comma N. Number of features, K is also one of the hyperparameter that you need to track, but usually it is 100, 50 or 200, something like that. Okay, and this is the number of tests per user. So number of test instances per user, he is taking it as 5. He is fixing. Okay, so not the percentage he is taking. Number of test instances per user is 5. And calling train test split, which returns rating matrix train data, rating matrix test data. Okay, and then randomly initializing U and V values here. So for that he is using normal distribution. So np.random.random, based on the normal distribution, he is initializing this U and V values. Once the U and V values are initialized, he is calling this matrix factorization that we have defined using the training data and these parameters U, V, and K. And after that, it will return the optimal U, optimal V, and the objective values. So now if you multiply this optimal U with optimal V transpose, you will get the predicted rating matrix. So this is NR is the predicted rating matrix. So once you get that, if any of the entries greater than 5, you make it 5, because our rating information is in between 1 to 5. If any rating less than 1, then you make it 1. So that way you scale these ratings. So once you get that, what next? You have to make the recommendation, right? So you have to find out the watched movies and the recommendation list. Okay, so wherever the user has not seen, you collect the entries, unobserved entries from the training data. Unobserved entries are the candidate items from which you have to make the recommendation, right? So, and you get the corresponding scores from the predicted matrix. Okay, so recommendation list score you are taking, and finally you are sorting them, sorting the list. Okay, and after sorting the list, you are taking top K movies, which is number of movies to recommend. Okay, so this is what you are picking as the recommendation movies and printing them from the movies. Like that location is you are giving this recommendation movie IDs and picking up them, right? And if you see, these are the objective values for each and every iteration, not each and every iteration, for every 100 iterations. So this is the initial value, and this is after 100 iterations. You can see it is reduced, and this is after 200 iterations, further reduced, 300 iterations, 400 iterations, and so on. You can see that it is constantly decreasing. There may be some place wherever slightly increasing and decreasing, and counting that if it is exceeds 5 counts, then we are terminating the algorithm. And these are the recommended movies. So this is what for we have scanned this movie file. So to show this movie names and movie IDs, right? So these are the 5 top K recommendations that we have made to the user. Okay. So that's all about the matrix recommend how to make the recommendation using matrix factorization. Okay, so you can evaluate it based on any of the evaluation measures that we have discussed. If you have any query in this code, please feel free to ask. I'll explain. Any query? Have you understood this? By the way?
Yes, to some extent understood. Abstractly you understood.
Okay, so please go through it one more time. You can, if you have any query, you can mail me. No problem. Anytime you can mail me. I'll reply. If you get any doubt at that, if you go through it again.
So
Okay.
this matrix factorization, the same code except for the recommendation part, ranking part, we can convolute it to. I mean, we can mold it to our classification problem also, no, sir? Except that recommendation part.
But here,
Features,
the parameters are different.
yes, sir.
If we got the matrix, no? There, how do you define a matrix? We don't have any matrix, no?
Yes, sir.
We don't have any users. But if you have users, no, like users and
Like
items,
social
then it
media.
again become again recommender systems only, no? If you talk about users and items.
Yeah.
Yeah.
Yes. Yes. Thank you, sir.
Yeah. But individual user, you can see it as a classification problem. If you take individual users, so for example, let me write it here. So for example, user 1 has consumed items 1, 2, 3 to 10, say for example. Okay, and user 1 has got some features, right? Like genre information, whether it is present or not, 100. And user 1 has given some rating for this one. Let's say it is some 4. And he has consumed item 2 and it has got some genres. Let's say 110 or something like this. He has given rating 3. So on. Rating 2, something like this. So this, if you see, for a single user, it is like a classification problem, no? In which you have features and the corresponding label. Features and the
Yes.
corresponding label. Okay, so you
Yes.
can apply any of the classification techniques and predict the classification for this. This comes under content-based recommender system. You can apply decision trees here and make the prediction. So for that, you have to construct one decision tree for each and individual user. And the decision, I mean, the prediction for that user based on the decision tree of him. I mean, for that particular user.
Yes.
Yeah. All right. Any other query? If not, we'll wind up. But please hold on for a